If you're watching this from the Arctic Circle, where it's negative 40 degrees, you've got nothing on the coldest place in the known universe, space, where somehow, despite being absolutely flooded with radiation from a burning ball of gas at 5,800 Kelvin, things reach temperatures so low, they approach absolute zero. Not 0 degrees Celsius. Absolute zero. Negative 273.15 degrees Celsius. Colder than your freezer. Colder than liquid nitrogen. So cold that atoms literally stop moving. Here's what will blow your mind. The sun is screaming energy at us every single second. Enough power hits Earth in 1 hour to power human civilization for an entire year. The sun could fit 1.3 million Earths inside of it. It's literally fusing hydrogen atoms in its core right now, releasing more energy than every nuclear bomb humanity has ever built, times 10 million, every single second. And yet, and this is the part that keeps physicists up at night, space is dark, silent, brutally, incomprehensibly cold. This isn't just a fun fact. This is a contradiction that, once solved, completely rewires how you understand the universe, your planet, and why you're even alive to ask this question. I'm going to show you why. But before we dive into the cold cosmic nightmare outside your bubble of warmth and light, I need you to do something for me. Hit that subscribe button. I know you've heard this 1,000 times, but here's why it actually matters. Every subscription tells. YouTube's algorithm that people care about real science explained in real terms. Not the dumbed down version. Not the mystical pseudoscience version. The actual, visceral, mind-bending truth. So I'm asking, subscribe. And tell me in the comments, what country are you watching from right now? What time is it where you are? I'm genuinely curious because this question, why is space so cold? It's universal. Whether you're in Tokyo at 6 p.m. or in London at 4 a.m., in Mumbai watching at midnight, or in São Paulo in the afternoon, you're all under the same sky, looking up at the same cosmic paradox. Right now, today, drop a comment. Let me know. I read every single one. Here's what we need to understand first, and this is where most explanations get it wrong. You've been thinking about heat incorrectly your entire life. Think of it like this. When you're in your living room and it's cold outside, your instinct is that cold flows in. Cold is a thing that travels. It isn't. There's no such thing as cold. What you're experiencing is the absence of heat. Cold is what happens when thermal energy leaves. This is the fundamental confusion that breaks most people's intuition about space. Heat isn't a substance. It's energy. It's the movement of atoms and molecules. When water boils, its molecules are vibrating intensely, colliding with each other at incredible speed. When water freezes, those same molecules are moving much more slowly, jiggling in place. Absolute zero, the theoretical minimum temperature, is when atoms stop moving entirely. They're frozen in place, literally. Quantum mechanics says they still have zero-point energy, but for our purposes, they're done vibrating. Now, here's where it gets interesting. And by interesting, I mean here's where we start bending your brain. Space itself isn't cold. Space is nothing. Think about that. Space has no medium. There's no air. There's no water. There's no stuff for heat to flow through. On Earth, heat travels 3 ways. Conduction atoms bumping into each other and passing thermal energy down the line. Convection hot fluids rising and cold fluids sinking. And radiation electromagnetic waves carrying energy across empty space. But in the vacuum of space, if there are no atoms bumping into each other, conduction is impossible. If there's no fluid, convection is impossible. Radiation is the only way heat travels in space. This is the first domino that falls. This changes everything. Think of space like this. It's the ultimate insulator. On Earth, a thermos is insulated with foam or air because those are terrible conductors. They prevent heat from flowing through them. Space is infinitely better at insulation because there's literally nothing for heat to conduct through. But space has a temperature. How? Here's the revelation that gets most people. Things in space don't have a temperature based on what surrounds them. They have a temperature based on the radiation they're absorbing and the radiation they're emitting. The Earth-bound satellites orbiting your head right now? The International Space Station? It's not cold because space is cold. It's cold, and it actually gets absurdly cold. Temperatures of negative 157 degrees Celsius on the night side, while the sunlit side can reach positive 121 degrees, because it's absorbing radiation on one side from the sun and losing radiation on the other side into the void. This is the foundation. This is where we start climbing. And if you're already feeling the cognitive dissonance, that's exactly right. You should be. Because the next section is where we introduce the star of this show. Here's what I want you to think about for the next 5 minutes. If heat can only travel by radiation in space, then what stops all the heat from the sun from warming everything up? Why doesn't the sun just cook the entire universe? That question will make sense in a moment. But first, you need to understand something about the sun's power that most people completely underestimate. Stick with me. This is where the paradox starts to make sense. Let me introduce you to 3 scientists who changed how we understand this. In 1905, a young Albert Einstein published a paper that would eventually lead him to understand that matter and energy are interchangeable. E equals mc squared. This wasn't just an equation. It was a cosmic key. It explained, for the first time, why the sun doesn't burn out in a few thousand years like people thought before. Because the sun isn't burning like a fire. It's fusing hydrogen into helium in its core, converting mass directly into energy at a rate that would make your head spin. In 1938, Hans Bethe, German-American physicist, figured out exactly how. He won a Nobel Prize for it in 1967, nearly 30 years later, because once they understood the process, everything changed. The sun is a thermonuclear reactor. A thermonuclear reactor that's been running non-stop for 4.6 billion years. And it has enough fuel to run for another 5 billion more. Here's what will blow your mind. Every single second, the sun converts 620 million tons of hydrogen into helium. Every second. That's a number so large, it stops meaning anything. To put it in perspective, that's the weight of about 110,000 elephants per second. And it's been doing this for longer than Earth has existed. Think of it like this. Your entire city's power consumption for a year? The sun generates that energy, everywhere, constantly. At noon on a clear day, about 1 kilowatt of solar radiation hits every single square meter of Earth's surface. That's roughly the power of a space heater. That's hitting your roof. That's hitting my roof. That's hitting the desert, the ocean, every square meter of every planet, every comet in the solar system. But then here's the catch that everybody misses: the sun's power falls off according to the inverse square law. This is where Stefan Boltzmann enters the chat. Actually, 2 guys, Stefan and Boltzmann. In 1879, they described that the intensity of radiation decreases with the square of the distance. It's not linear. It's not that as you double your distance, the heat halves. No. As you double your distance, the heat becomes 1/4 as strong. Triple the distance? 1/9 the power. Go 10 times farther away? 1/100th the power. So here's what's happening. The sun is streaming energy outward in all directions. It's like a cosmic light bulb, and we're lucky enough to be close enough to bask in its glow. But space is so big, so incomprehensibly vast, that almost all of that energy is just going nowhere, flying into the void, missing everything. Think of it like this. Imagine you're in a stadium with 1,000 people. One person is standing in the center with a flashlight, shining it in all directions equally. How much of that light hits you? It doesn't hit very much, because it's spread out over the entire stadium. The farther you are from the light, the dimmer it is. Now imagine the stadium is the size of an astronomical unit, the distance from Earth to the sun. 150 billion kilometers. Still think the light is bright? In the vacuum of space, between stars, between galaxies, there's nothing absorbing that radiation most of the time. It's just traveling through nothing. And nothing is a terrible medium for absorbing heat. Or rather, it's a perfect medium for failing to absorb heat. Here's the mind-bending part. The temperature of space isn't low because the sun is far away. The temperature of space is low because there's nothing there to be heated in the first place. We're about to explore what is in space, and this is where it gets weird. So here's my question for you. If the sun is powerful enough to warm a planet from 93 million miles away, why doesn't space between the sun and Earth get heated up? Why is the vacuum itself so cold? Stick around because the answer involves something that most people forget about the space between stars. And it's about to rewrite your understanding of the universe. I want to introduce you to someone most people have never heard of. Herschel, William Herschel. In 1800, he was experimenting with sunlight, splitting it through a prism, and he held a thermometer in each color of the rainbow. Red, orange, yellow, green, blue, violet. But he also held it just beyond the red light, where there was supposedly nothing. And the thermometer went up. He discovered infrared radiation. He discovered that there's energy we can't see with our eyes. Invisible heat. Fast forward to 1895, and Wilhelm Röntgen discovers X-rays. Suddenly, we realize that the electromagnetic spectrum is huge. Visible light, the stuff our eyes can see, is just a tiny sliver sandwiched between infrared and ultraviolet. It's like the entire universe is broadcasting in 1,000 different radio channels, and we've only tuned into one. Now, here's what space actually contains. Space isn't empty. That's been the biggest myth. There's about 1 hydrogen atom per cubic centimeter in interstellar space. 1 atom per cubic centimeter. In a room-sized volume, you might have billions of atoms. In the same room-sized volume in deep space, you'd have maybe 1 or 2 atoms, and they'd be so spread out, they'd almost never collide. Think of it like this. If Earth's atmosphere were a crowded subway train, with billions of molecules packed together bumping into each other constantly, then interstellar space is like being in an enormous, empty stadium where one person walks in every few days. It's so sparse that it's effectively a vacuum. But here's what's really in space, and this is crucial: radiation. There's the cosmic microwave background radiation. In 1964, Arno Penzias and Robert Wilson, 2 radio engineers, were trying to eliminate static from their antenna, and they couldn't. No matter what they did, there was this persistent hiss. They thought it was pigeon droppings on their antenna. Seriously, they almost gave up. But they didn't, and they discovered they were picking up the afterglow of the Big Bang itself. The universe was still humming at a temperature of 2.7 Kelvin. That's about minus 270 degrees Celsius. This is the background radiation that fills all of space. Every cubic meter of space, even the coldest, darkest corner, is bathed in this radiation. But that radiation is old. It's been cooling down for 13.8 billion years as the universe expanded. And that's part of why space is cold. Think of it like this. Imagine the universe is a balloon. When the universe was born, it was incredibly hot and dense. As it's expanded, and it's still expanding, it's cooled down. That radiation is still there, but it's been redshifted, stretched out into longer wavelengths, converted into lower energy photons. It's like the universe itself is cooling. The background temperature of space is determined by this ancient radiation. Here's something that might break your brain. The coldest place in the universe isn't in space. It's in a laboratory on Earth. In 2003, scientists at MIT cooled a cloud of sodium atoms to 0.2 million Kelvin. That's 3 billionths of a degree above absolute zero. In 2000, scientists in Finland hit 0.1 nanokelvin. That's 0.1 billionths of a degree above absolute zero. The coldest place is literally a room full of lasers and magnets. But space? Space is a toasty 2.7 Kelvin, relatively speaking. It's warmer than MIT's lab. So let me ask you, if space has this background radiation, if space has this temperature, why do things freeze so fast? Because the radiation in space is old radiation. It's low energy. It's infrared and microwave radiation mostly. And here's the kicker. When things are in space, they're absorbing this low-energy radiation from the cosmic microwave background while simultaneously radiating away any thermal energy they have at higher frequencies. A satellite in space? It's absorbing thermal radiation at microwave frequencies. But if it's a metal satellite, it's radiating away thermal energy at infrared and even visible light frequencies if it gets hot enough. It's losing energy faster than it's gaining it from the thin cosmic soup around it. This is the first piece of the paradox solved, but we're about to go deeper. Because here's what really happens. Things in space don't just lose heat through radiation. They also encounter something that most people never think about. Next section, we're talking about the cosmic wind, and this is where physics gets genuinely strange. Remember when I said space is a vacuum and there's only one atom per cubic centimeter? That's not completely true. And here's where it gets weird. The sun doesn't just send out light and heat. It sends out particles, charged particles, mostly protons and electrons and some heavier ions. This is called the solar wind. It's a constant stream of plasma-ionized gas flowing outward from the sun at speeds of 300 to 800 kilometers per second. In 1959, someone suggested this should exist. E. N. Parker, one of the most prolific physicists of the 20th century who lived to be 94 and remained actively publishing until his death, predicted that the sun would constantly lose mass in this way. Other scientists said he was crazy. They said, "There's no way the sun can escape its own gravity like that. Parker's insane." He wasn't insane. In 1962, Mariner 2 sent back the first data confirming it. The solar wind is real. It's constantly flowing outward. It's carrying away millions of tons of solar matter every single day. Think of it like this. The sun is a campfire, and the solar wind is the smoke. Not actually smoke, but the analogy works. The fire of the sun is shooting out particles in all directions. These particles are traveling at insane speeds, and they're carrying energy with them. Here's what will blow your mind. The solar wind creates a protective bubble around our solar system called the heliosphere. It's not actually a sphere. It's more like a teardrop shape because of the motion of the sun through the galaxy. But essentially, it's a buffer zone. The solar wind pushes against the interstellar medium, the thin gas between stars, and creates a boundary. Beyond that boundary, in the interstellar medium, things are cold, really cold, about 10 Kelvin on average, minus 263 degrees Celsius. That's where space gets truly brutal. That's where molecules freeze solid instantly. But inside the heliosphere, near Earth, we're getting radiation and charged particles and protection from the deepest cold. We're in a warm bubble, relatively speaking. The solar wind is the sun's shielding. It's pushing back against the cosmic radiation and interstellar cold. It's protecting us. And it's also why space near Earth gets its temperature characteristics. Here's a mind bender. The temperature of the solar wind near Earth is about 300,000 Kelvin. That's 300,000 degrees. Yet astronauts feel cold in space. How? Because the solar wind is so sparse. There's not much mass to it. Temperature is really about molecular motion, how fast particles are moving, but it's usually measured in bulk. When you measure the temperature of the solar wind, you're measuring the average velocity of those particles. But there are so few of them that they carry almost no energy in bulk. It's like the difference between a few fast-moving tennis balls and a pool of warm water. The tennis balls are moving faster, but the water has way more thermal energy because there are trillions of water molecules. So space is a paradox. It can be simultaneously hot and cold. A thermometer in space would read one temperature based on radiation. But if you measured thermal energy density, the actual amount of heat per unit volume, it would be incredibly low. Think of it like this. Imagine a concert where millions of people are quietly humming at different pitches, and one person is screaming at the top of their lungs. The screaming person has high amplitude, but they represent one voice out of millions. The overall sound pressure might be lower than you'd expect. The solar wind is like that one person screaming. High velocity, high temperature when measured in motion, but very little actual thermal energy because there's not many particles. Okay, so we've established that space near Earth is actually surprisingly warm in one sense and incredibly cold in another sense. But we haven't explained the main event yet. In the next section, we're about to talk about the thing that absolutely dominates the temperature experience in space, the absence of air, the thermodynamic properties of vacuum. And trust me, this is where the full paradox finally resolves. Because it turns out that cold in space is completely different from cold on Earth. Astronauts wear spacesuits, expensive, sophisticated spacesuits, not because they'll freeze solid in seconds like Hollywood tells you. That's actually not quite right. But because they need protection from something else entirely that makes space profoundly cold to any living organism. Let me break down what actually happens to an unprotected human in space. First, the pressure difference. At sea level on Earth, you're experiencing about 101 kilopascals of pressure. That's the weight of the entire atmosphere pressing down on you. In space, there's no atmospheric pressure. Your body pressure is suddenly uncontained. Fluids in your body would want to expand. Your saliva would boil. Your blood would start to boil. Not because it's hot, because without external pressure, the vapor pressure of water means it converts to steam. This would happen in about 90 seconds. You'd lose consciousness in about 15 seconds from lack of oxygen. But that's not freezing. The actual cold comes from evaporation. And this is where we hit profound physics. Think of it like this. When water evaporates, molecules at the surface escape, but those molecules are the fastest moving ones. When the fastest molecules leave, the average speed of the remaining molecules drops. Temperature drops. It's why sweating cools you down. The water on your skin evaporates, taking away your body heat in the process. In space, with no atmospheric pressure, all the moisture on your body, on your skin, in your lungs, the water in your sweat would evaporate rapidly. This evaporation would pull tremendous amounts of thermal energy from your body. You'd cool down extremely quickly, not infinitely fast, but very fast. You'd lose body heat orders of magnitude faster than in the coldest Arctic conditions. And this is the real kicker, you wouldn't freeze solid. You'd lose consciousness from hypoxia long before your core temperature dropped enough for your organs to fail. However, the sensation of cold in space would be overwhelming because of something called radiative cooling. Your body, at normal body temperature of 37 degrees Celsius, is radiating thermal energy constantly. In Earth's atmosphere, that radiation is absorbed by air molecules and re-radiated back, creating a sort of thermal recycling. In the vacuum of space, that radiation just escapes into the void. Nothing is there to absorb it or re-radiate it back to you. You're losing thermal energy in one direction only, outward. Here's what will absolutely destroy your intuition. The thermometer doesn't measure what you'd feel. The ambient radiation temperature of space from the cosmic microwave background is 2.7 Kelvin. But that's incoming radiation. It's old, low energy. Meanwhile, your body is radiating in the infrared at a much higher temperature. You're losing energy faster than you're gaining it. You're a hot object in a cold radiation field. The net heat flow is outward. That's what we mean by space is cold. It's not that the ambient temperature is low. It's that the radiation balance is catastrophic for warm objects. Think of it like this. Imagine you're in a room where the walls are at absolute zero. The room's temperature is 0 Kelvin according to the thermometer. But the walls are absorbing all the infrared radiation you emit. They're not emitting any back. You're in thermal equilibrium with nothing. You're radiating away. In space, the cosmic microwave background is like those walls, incredibly cold, absorbing your radiation, emitting almost nothing back. This is the genius of space as a thermos for spacecraft. When SpaceX launches a Falcon 9, the rocket, the steel, the fuel starts incredibly hot from the launch. But as it gets to space, even though there's solar radiation hitting it on one side, on the night side, it's radiating away heat with nothing to absorb that radiation. It reaches equilibrium at a temperature determined entirely by the balance between incoming radiation and outgoing radiation. The International Space Station reaches equilibrium temperatures of about 100 to 120 degrees on the sunlit side and negative 150 degrees on the night side. Not because the vacuum itself is that temperature, but because that's the temperature at which the incoming and outgoing radiation are balanced. So here's what we've learned so far. Space isn't cold in the traditional sense. Space isn't anything in the traditional sense because there's nothing there. But for objects in space, cold means losing heat via radiation faster than painting it. Next, I want to talk about something that makes this even weirder. What about places in space that are actually cold, not by radiation, but by the actual absence of thermal energy? We're about to dive into something that kept me up at night when I first learned about it. There are places in space that are actually genuinely, legitimately cold in a way that breaks all the assumptions we've made so far. Between the stars, in regions of the galaxy far from any star, there are clouds of gas and dust. Molecular clouds. They're some of the most fascinating structures in the universe, and they're also some of the coldest places that occur naturally in space. These clouds reach temperatures of 10 Kelvin, minus 263 degrees Celsius. At these temperatures, simple molecules like carbon monoxide freeze out. Hydrogen itself is mostly in its molecular form, H2. At these temperatures, the hydrogen cloud is essentially solid ice. You could touch it. Well, if you could survive in space, which you can't, but theoretically, why are these clouds so cold? Because they're far from any star. The primary heat source in any region of space is radiation from nearby stars. In a molecular cloud, the nearest star might be light years away. The radiation from distant stars is incredibly weak. Meanwhile, these clouds are radiating away their own thermal energy into the cosmic void, and there's nothing replenishing it. In 1995, observations from the Hubble Space Telescope by Kenneth Sembach and others revealed that molecular clouds contain some of the most complex chemistry in the universe. In one cloud, over 100 different molecular species have been detected: carbon monoxide, water ice, ammonia, formaldehyde. The cold preserves these molecules. It slows down reactions. It creates a sort of cosmic freezer where chemistry can progress on geological timescales. Think of it like this. The coldest parts of space are like the deep ocean trenches of Earth. Life there exists in extreme conditions, with crushing pressure and darkness. In space, these molecular clouds exist in extreme conditions of vacuum and cold, and chemistry, the kind that eventually leads to life, happens anyway. Here's what will absolutely reframe your understanding of the universe. The very elements that make up your body were created in these molecular clouds. Carbon, oxygen, nitrogen, the building blocks of life, were synthesized in stars and then distributed through space in stellar wind and explosions. They collected in molecular clouds where they were cold preserved for millions of years, undergoing complex chemical reactions. Eventually, our solar system formed from one of these clouds. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it spent time in a molecular cloud at 10 Kelvin. You are, quite literally, made of recycled cosmic material that spent time in one of the coldest furnaces of chemistry the universe has to offer. And here's the thing nobody talks about. These clouds are also where stars are born. When a molecular cloud collapses, usually triggered by the shock wave from a nearby supernova region's compress. Density increases, pressure increases, temperature increases. A star is born. The cold, preserved chemistry becomes the seed for new suns and new planets. So space isn't just cold and empty. In the places where chemistry and star formation happen, it's a cradle. It's a womb. The cold isn't the enemy of creation. It's the prerequisite. But wait, there's more weird. And it gets more wonderful. The Boomerang Nebula, discovered in 1995 by Keith Taylor and Samir Patel, is the coldest object in the universe that we know of, 1 Kelvin. Some measurements suggest even colder, around 0.5 Kelvin, colder than the cosmic microwave background. How is that possible? Because it's rapidly expanding. It's cooling down adiabatically. The nebula is expanding so fast that it's doing work on its environment, pushing outward. That work is energy. The nebula is using its own thermal energy to do that work, so it's cooling as a result. Think of it like this. When you pump up a bicycle tire, the pump gets hot. Compressing gas heats it. The reverse is also true. Expanding gas cools. The Boomerang Nebula is the universe's ultimate example of the reverse process. We are approaching something profound. We've talked about why space is cold, but we haven't talked about what that cold means for anything. Next, we need to understand what the true advantage of being in space actually is, and why organizations like NASA and SpaceX are actively trying to use this cold as a tool. This is where the universe's greatest feature starts to make sense. I want to ask you a personal question. Have you ever thought about why you need sleep? Your brain generates heat. Your heart generates heat. Every cell in your body is burning calories and creating thermal energy as a byproduct. During the day, this heat accumulates. By night, your body needs to cool down. Your skin flushes. You sweat slightly. You lie down horizontally, so your body's surface area is more exposed to air for cooling. You sleep in a cool room, so there's a gradient your body heat flows outward to the environment. This is a fundamental constraint of biology. All warm-blooded animals face it. We need to dispose of heat constantly. If we can't, our core temperature rises. We suffer heat stroke. We die. Now imagine if you didn't have that problem. Imagine if you could radiate away your body heat infinitely fast into an environment that was incredibly cold. Here's what will blow your mind. In space, the ultimate heat sink, some of the most advanced cooling systems ever developed by humanity, are passive radiators. They're just flat panels made of specific materials that radiate infrared heat into the cosmic void. The International Space Station has these. Large flat panels with specific coatings that maximize infrared emissivity. No active cooling needed. Just the physics of thermal radiation. Think of it like this. On Earth, if you want to cool something, a computer chip, a server farm, a power plant, you need moving water or air. You need circulation. You need energy. In space, you just need a panel facing away from the sun. The cold of space becomes your cooling system. But this is where it gets philosophical, because this actually affects you right now. Computers generate heat. Your laptop generates heat. Modern computers are getting faster and smaller, which means they're generating more heat per unit volume. They need better cooling. Data centers, the servers that run your email, your social media, your cloud storage, they use about 3% of the world's electricity, and most of that goes to cooling. 3% of global electricity, just to cool down computers. What if we could move that computing to space? What if instead of cooling servers on Earth with energy-intensive air conditioning and water systems, we put them on satellites where passive radiators could do the job? This isn't science fiction. In 2023, researchers at MIT proposed the feasibility of space-based data centers cooled entirely by thermal radiation into vacuum. Companies are starting to seriously consider this. Here's something that might change how you think about your future. Your existence in the next 50 years might depend on learning how to use the cold of space as a resource. Climate change is causing global temperatures to rise. We need more cooling capacity to run the technology we depend on. The coldest, most efficient cooling resource available is the vacuum beyond our atmosphere. It's not just a curiosity. It's potentially a necessity. This connects to another issue. You produce heat. Your body is constantly radiating thermal energy. In a crowded city, with billions of people all radiating heat, all running computers and air conditioning systems that generate waste heat, entire urban areas become heat islands. Phoenix is degrees hotter than surrounding desert because of human activity. Cities across the planet are becoming uninhabitable during summer months because of heat. What if there was a way to radiate that heat directly into space instead of trapping it in the atmosphere? There are scientists working on this right now. Radiative cooling materials that work on Earth, sending heat through the atmosphere to space. Passive radiators that require zero energy. They're already being tested. This is personal. The cold of space, which seems like an abstract curiosity, is actually deeply relevant to whether you'll have a livable climate in 2050, whether your city will be habitable in summer, whether you'll have the computing power and energy efficiency you need. Think of it like this. The cold of space is Earth's biggest air conditioner. We're only just starting to learn how to use it. This is when things get personal and philosophical. We've talked about the physics. We've explained why space is cold. We've explored what it means. But I haven't talked about you yet. How does any of this change your understanding of your place in the universe? Next section is about to get deep. We're about to talk about the fundamental misunderstanding humanity has about our planet and why space being cold is a profound revelation about our cosmic situation. Earth is not special because it's in the middle. It's special because it's in the only place in our solar system where the thermal dynamics work out in our favor. Every exoplanet we discover gets classified by its position relative to its star. There's a concept called the habitable zone, or sometimes the Goldilocks zone. Not too hot, not too cold, just right. Scientists calculate this by figuring out where a planet would be if it received enough thermal radiation to have liquid water. Venus is too close to the Sun. It's 50 degrees hotter than Mercury, despite being farther away because of a runaway greenhouse effect. The atmosphere is so thick and full of carbon dioxide that it traps heat like a pressure cooker. Surface temperature, 464 degrees Celsius. Hot enough to melt lead. Mars is too far. It receives maybe 40% of the radiation Earth does. Its surface temperature averages negative 60 degrees Celsius. The atmosphere is so thin, it might as well be vacuum. Water is frozen solid in underground ice. Earth is exactly in the middle. We receive just enough radiation from the sun to maintain liquid water, liquid oceans, the ability for chemistry to happen at reasonable speeds. Our atmosphere traps some heat through the greenhouse effect, keeping us warm enough. We're not cooking in a pressure cooker. We're not frozen solid. Think of it like this. The sun is a heater. The cosmic void is a cold sink. Every planet is sitting between the two, trying to maintain equilibrium. Venus cranked up the greenhouse effect so high that it lost that equilibrium. Mars didn't have enough atmosphere to maintain equilibrium. Earth hit the sweet spot. But here's what will blow your mind. If space weren't so cold, Earth couldn't exist as it does. Think about thermal equilibrium. The Earth receives energy from the sun. If Earth is to maintain a stable temperature, it has to radiate away the same amount of energy it receives. Where does it radiate that energy? Into space. It radiates it into the cold cosmic void. The thermal balance of the entire planet depends on the fact that space is cold enough to accept that radiation. If space were warmer, if the cosmic microwave background were at, say, 50 Kelvin instead of 2.7 Kelvin, Earth would heat up. The planet would reach a new equilibrium at a higher temperature. And that temperature would be incompatible with the existence of life as we know it. Here's the revelation. Your existence right now depends on the universe being cold. You are alive because the universe expanded after the Big Bang and cooled down. You are alive because space is cold. Because there's a vast thermal sink available at 2.7 Kelvin to accept the excess heat your planet generates. Because your planet found the exact position where incoming and outgoing radiation balance to create the conditions for chemistry, for life, for you. This is the cosmic rearrangement. We think of space as cold and harsh and deadly. And it is, but we're only here because it is. The very harshness of space, the vacuum, the cold, these are the conditions that make our temperate, habitable world possible. We're on an island of warmth surrounded by an ocean of cold, and we're only aware of that ocean's existence because we've built machines to measure it. For millions of years, humans looked at the night sky and wondered. We felt the starlight on our skin. We experienced the contrast between the heat of the sun and the chill of space through our instruments. But we didn't understand the mechanism. We didn't understand that we were looking at the very framework that permits our existence. Think of it like this. You live in a house that's warm inside. Outside, there's a winter storm. You're comfortable inside because of the temperature difference. If the storm were warmer, the house wouldn't feel as cozy. The contrast is what makes comfort meaningful. Earth is comfortable because of the contrast with space. We exist because of that contrast. And here's the kicker. That thermal contrast is shrinking. Human activity is adding greenhouse gases to the atmosphere. We're reducing the efficiency of heat radiation to space. We're slowly reducing that thermal gradient. We're making Earth hotter because we're making it harder for our planet to radiate its excess heat into the cold cosmic sink. Climate change, fundamentally, is about disrupting the thermal balance between Earth and space. It's about making space less accessible as a heat sink. And understanding why space is cold, understanding that mechanism, is the first step to understanding how we're breaking it. This is getting profound. We've moved from physics to personal relevance to climate implications. But we haven't explored the deepest question yet. What does this tell us about our cosmic situation? What does this tell us about the universe's fundamental nature? Next section gets into philosophy and implications that might change how you see everything. Entropy, the second law of thermodynamics. Disorder always increases. Things fall apart. Heat spreads out. Order requires energy. The universe is running down. 13.8 billion years ago, the Big Bang happened. The universe was incredibly hot, incomprehensibly hot, and incredibly ordered. Everything was jammed together in an infinite density point. Then it expanded. It cooled down. It's still cooling down. The cosmic microwave background is evidence of that cooling. 2.7 Kelvin is the remnant temperature of a universe that was once hot enough to prevent atoms from existing. Every particle was radiation. Now, space is cold, and that cold is the signature of the universe's aging. Think of it like this. Imagine a coffee cup. You pour hot coffee into it. Steam rises. You walk away. After an hour, the coffee is room temperature. After a day, it's the same temperature as everything around it. It's in thermal equilibrium. The coffee hasn't become more ordered. It's become more disordered. Entropy increased. The universe is that coffee cup. Space is cold because the universe is old. The universe is running down. But here's where it gets profound. This means everything, including you, is part of a process that's fundamentally about increasing disorder. You are a system of incredibly low entropy. Your body is organized. Your cells are ordered. Your consciousness emerges from that order. But maintaining that order requires energy. You eat food energy from the sun, captured by plants. You use that energy to maintain your low entropy state against the universal tendency toward disorder. Everything you do, every thought you have, every second you're alive, you're temporarily creating order in an increasingly disordered universe. And when you die, that order dissipates. Your body decays. Your atoms scatter. You return to thermal equilibrium with the universe. This isn't sad. This is profound. Here's something that might change your perspective on your entire existence. The reason space is cold is the same reason you die. Both are expressions of entropy. Both are consequences of the second law of thermodynamics. Space is cold because the universe is expanding and dissipating its energy into an ever larger volume. You will die because entropy always increases, and systems of low entropy like living beings can only be maintained temporarily by expending energy. The cold of space is the heat death of the universe in progress. And you conscious, alive, aware are a temporary eddy in that flow. You're a system that's momentarily fighting entropy, and you're destined to lose that fight. And here's the thing, that's not a reason for despair. That's a reason for awe. Think about it. We are stardust. The carbon in your body, the calcium in your bones, the iron in your blood, all synthesized in stars. We are the universe becoming conscious of itself. We are entropy becoming aware of itself. The universe is running down, and in the process, it created beings capable of understanding that process. That's not tragic. That's miraculous. Here's what Carl Sagan understood. The cosmos gave rise to life, and life gave rise to consciousness. We are part of the cosmos examining itself. The cold of space isn't a barrier to understanding. It's a truth about how the universe works, and that truth is available to us precisely because we exist at this moment in cosmic history. After the universe has cooled enough for atoms to exist, for stars to form, for planets to exist, for life to emerge. If space were warm, if the universe hadn't cooled, none of this would exist. We're alive in the window between the hot Big Bang and the cold heat death of the universe. We're conscious during the Goldilocks era of cosmic history. Okay, we're getting deep. We've covered physics, personal relevance, climate implications, and cosmic perspective. But I haven't talked about something crucial, the edge of our knowledge. There are things about space and cold that scientists still don't understand. There are mysteries, puzzles, questions that keep cosmologists up at night. In the next section, we're going beyond what we know into what we're still trying to figure out. In 1998, two teams of astronomers, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, were observing distant supernovae. They were trying to measure how fast the expansion of the universe was slowing down. They expected the expansion to be slowing. Gravity pulls everything together. After the Big Bang threw everything apart, gravity should be pulling it back. The universe should be decelerating. But the data said something shocking. The universe's expansion was accelerating. The universe isn't just expanding, it's speeding up. And we have no idea why. They called the cause dark energy. Not because it's dark in the sense of not giving off light. Dark in the sense that we don't know what it is. It's about 70% of the entire universe's energy mass content, and we don't know what it is. Think about that. 70% of everything in the universe, and it's a mystery. Perlmutter, Schmidt, and Rees won the Nobel Prize in Physics in 2011 for this discovery. But winning a Nobel Prize for discovering something doesn't mean we understand it. It means we discovered that we don't understand it. One theory is that dark energy is the cosmological constant, a property of space itself, often associated with vacuum energy. According to quantum mechanics, empty space isn't actually empty. It's seething with virtual particles constantly popping in and out of existence. These virtual particles might have energy. That energy might be what we call dark energy. But here's the puzzle. The vacuum energy density that quantum mechanics predicts is off by a factor of 10 to the 120. That's a 1 followed by 120 zeros. It's one of the largest discrepancies in physics. Either our understanding of quantum mechanics is wrong, our understanding of general relativity is wrong, or something else is going on entirely. Here's what might shatter your mind. the cold of space might be intimately connected to the mystery of dark energy. As the universe expands and cools, more space appears. If space itself has energy, then creating more space might be adding energy to the universe. That energy accelerates the expansion. That acceleration means the universe is cooling even faster. We don't know if this is true, but it's one of the leading ideas. The cold of space and the acceleration of the universe might be two symptoms of the same phenomenon, the properties of empty space itself. Think of it like this. Imagine a rubber balloon being inflated. As it gets bigger, the surface area increases. If every square inch of the balloon's surface had intrinsic energy, then inflating the balloon would be adding energy to the system. That's a bit like what dark energy might be doing to space itself. But we're speculating here. This is the frontier of physics. We're in the territory of not quite knowing. Here's what this means for the future. The universe will continue to expand and accelerate. The galaxies around us will move farther away. The light from distant galaxies will redshift into longer and longer wavelengths until they disappear entirely from our observation. The cosmic microwave background will cool further. Space will become even colder. In trillions of years, the universe will be so cold and so expanded that temperatures will approach 0 Kelvin everywhere. Stars will have burned out. Black holes will have evaporated through Hawking radiation. Protons will have decayed if they decay at all. We don't even know. The universe will be dark and cold and essentially empty. That's the heat death of the universe. And we're living in the brief era between the hot Big Bang and the cold cosmic end. We're alive during the only time when the universe is warm enough for chemistry, for life, for consciousness. This is where I need to bring us back down to Earth, literally. We've been traveling through cosmic scales, through mysteries at the edge of human knowledge. But there's one more thing I need to talk about: the immediate, visceral, personal implications of why space is cold. What does this mean for your life in 2026 and beyond? Stick around because the next section is about you. I want you to pause for a moment and think about something simple. Why does it feel good to step outside on a hot day when there's a breeze? It feels good because that breeze, that air, is carrying away your body heat. Your body is dumping excess thermal energy into your environment, and that feels pleasurable. It feels like relief. Now imagine if you could do that infinitely fast. Imagine if, whenever you overheated, you could simply radiate that heat away into an environment that would accept it immediately with zero thermal resistance. That's what space does. But let me make this personal in a different way. You are here, alive, conscious, aware, reading these words or listening to these words, precisely because space is cold. Not metaphorically, literally. Here's the chain of cause and effect. Universe expanded and cooled after the Big Bang. This cooling allowed atoms to exist. These atoms collected into vast clouds. These clouds cooled further down to temperatures of 10 Kelvin. In that cold, complex chemistry happened. Carbon-based molecules formed. Planets formed. Life emerged. You emerged. Your consciousness emerged. Every step of that chain of events depended on the universe being cold. If the early universe had remained hot, none of this would exist. If space weren't cold today, Earth's thermal balance would be disrupted, and life as we know it would cease to exist within decades. Think of it like this. Your body is like a little campfire in the dark. The dark around you is space. That darkness, that cold is necessary for your fire to exist. Without the contrast, without the vastness of cold to radiate your heat into, your fire would go out. But there's something else, something deeper. Right now, in 2026, you're at a pivotal moment in human history. You're living in the era of climate change. You're living in the era where humanity has become aware that it's disrupting the thermal balance of its own planet. You're living in the era where we're starting to ask, how do we sustainably manage the heat we generate? And the answer might lie in understanding space, in learning how to use that cold as a resource. in developing technologies that radiate waste heat into space, in eventually moving energy-intensive operations, data centers, manufacturing, computing to orbital platforms where the cold is unlimited. This isn't theoretical. This is happening. NASA is developing radiative cooling systems. Private companies are planning space-based solar power stations that would beam energy to Earth and radiate their waste heat into space. Within your lifetime, you might see manufacturing happen in orbit, cooled by the vacuum. You might see your climate problem partially solved by learning to use the cold of space. Here's something that genuinely might change your perspective. The cold of space, something that seems impossibly distant and abstract, is about to become one of humanity's most important resources. The practical reason we're learning why space is cold, the practical reason this matters, is that learning it now, understanding the thermal physics of vacuum, is training ground for the next chapter of human civilization. We're about to become a spacefaring species. Not like the movies show it, with huge space stations and people floating around casually. More fundamentally, we're going to start moving human civilization's energy-intensive processes off-world because Earth can't sustain them sustainably. And when we do, we'll be using the principles we've discussed today. Think of it like this. Your ancestors learned to use fire. That transformed their civilization. Later, humans learned to harness wind and water. That transformed civilization again. Then fossil fuels. Then electricity. Now, we're learning to harness the cold of space. That's going to transform civilization again. And you're going to witness it. We're almost at the end of this journey. We've traveled from the initial paradox, how can space be cold when the sun is hot? Through physics and personal implications. But I need to tie this all together. I need to give you a framework for understanding everything we've discussed and how it connects to something even larger. That's coming next. Let me map out the full structure of understanding we've built over the past 2 hours. We started with a paradox. Why is space cold when the sun is hot? The answer we discovered wasn't a single reason. It was a web of reasons, each one connecting to every other. Reason 1, the inverse square law. The sun's power falls off with distance. At Earth's distance, the sun is intense. At the distance of interstellar space, it's negligible. But that's not why space is cold. That's just why far away is cold. Reason 2, vacuum's thermal properties. Heat can only travel by radiation in space. Without a medium, conduction and convection don't work. For objects in space, temperature is determined by the balance of incoming and outgoing radiation, not by contact with a medium. This is profound because it changes what temperature means. Reason 3, the cosmic microwave background. The universe is bathed in ancient radiation from the Big Bang. That radiation is 2.7 Kelvin. That's the baseline temperature of space. Objects in space that emit radiation at higher temperatures will cool down as that radiation escapes into space. Reason 4, entropy and cosmic evolution. The universe is running down. It's expanding. It's cooling. The cold of space is a consequence of billions of years of expansion and entropy increase. We're living in an era when the universe is old enough and cold enough for life to exist, but young enough that stars still burn and planets still host biology. Reason 5, the thermal balance of habitable planets. For a planet to support life, it must maintain thermal equilibrium. It receives energy from its star. It must radiate that energy into space. The cold of space is essential for that radiation to happen efficiently. Without it, planets would heat up to uninhabitable temperatures. Reason 6, dark energy and cosmic acceleration. Something unknown dark energy is accelerating the expansion of the universe. This acceleration means the universe is expanding faster. Space is getting larger, and the thermal energy is spreading out over an ever greater volume. Space is getting colder. Dark energy might be connected to the properties of vacuum itself, which connects back to reason 2. These 6 reasons aren't separate. They're woven together. They're manifestations of the same underlying physics. Think of it like this. Imagine you're looking at a tapestry. You can trace individual threads. One thread is the inverse square law. Another is the cosmic microwave background. Another is entropy. But if you step back and look at the whole tapestry, you see that all the threads connect. They form a single image. The image is how the universe works. The cold of space isn't a fact, it's a truth. It's something that emerges from the basic laws of physics, operating in an expanding universe. Here's what ties it all together. The reason space is cold is the same reason you exist. The same reason your planet exists. The same reason the universe hasn't already reached its final heat death. It's all entropy. It's all the second law of thermodynamics. The universe started hot and ordered. It's running down, cooling, becoming more disordered. We live in the era between the hot beginning and the cold end. We're alive in the window of opportunity that entropy has given us. And understanding why space is cold is understanding why that window exists. It's understanding the fundamental framework of reality. Think of it like this. Physics is like a story. Each chapter builds on the previous ones. The inverse square law is a chapter. Thermodynamics is a chapter. Entropy is a chapter. General relativity is a chapter. Quantum mechanics is a chapter. The story they tell together is the story of the universe. The cold of space is the plot point that explains everything that comes after it. And you're reading the story right now. You're at the part where the universe is cooled enough for consciousness to emerge. And that consciousness is understanding the mechanism that created it. That's the climax of the story. That's now. We're arriving at the conclusion. We've explained the physics. We've shown the personal relevance. We've mapped out the cosmic framework. But there's one final thing I need to tell you. One final thing that brings this all home. It's about you, your significance, and what happens after you finish this video. That's the last section. When I started this video, I asked you a question. Why is space so cold when the sun is hot? By now, you understand that the question itself contains a misconception. Space isn't cold in the way your kitchen is cold when you leave the freezer door open. Space isn't cold in the way winter is cold. Space is something stranger than that. Space is cold because it's nothing. Space is cold because heat travels through it by radiation only. Space is cold because the universe has been expanding and cooling for 13.8 billion years. Space is cold because everything in it is running down, entropically, toward a state of greater disorder. But understanding that answer changes something in you. It fundamentally rewires how you see your place in the universe. Think about what we've covered. You learned about scientists. Albert Einstein revolutionizing our understanding of energy. Hans Bethe explaining the sun. Stefan and Boltzmann quantifying radiation. Ian Parker predicting the solar wind. William Herschel discovering infrared light. Arno Penzias and Robert Wilson stumbling upon the cosmic microwave background. These weren't just names and discoveries. These were human minds working across centuries, gradually assembling the pieces of the puzzle. And now you have the whole picture. You learned about the physics, the inverse square law, thermal dynamics, radiation, entropy, the cosmic microwave background. You learned why heat travels the way it does and why the vacuum is the ultimate insulator. You learned that cold is a phenomenon that depends on what you're measuring and from what reference frame. You learned about the implications. Climate change is fundamentally about disrupting the thermal balance between Earth and space. The future of human civilization might involve harnessing the cold of space as a resource. The very existence of habitable planets depends on that cold. The existence of you depends on it. You learned about the cosmic perspective. The universe is running down. You are a temporary eddy of low entropy in a river flowing toward heat death. You are stardust become conscious. You are the universe understanding itself. That's not poetic metaphor. That's physics. That's truth. And now, Having understood all of this, you face a choice. You can close this video and go back to your day. You can treat this like entertainment, intellectually stimulating, but ultimately separate from your actual life. That's an option. Many people choose it. And I hope this is what you choose. You can let this change you. Here's what I mean. Understanding why space is cold is understanding something fundamental about reality. It's understanding that seemingly disconnected phenomena, entropy, radiation, planetary climate, human consciousness, are all expressions of the same underlying laws. That understanding is powerful. It's the kind of understanding that, once you have it, you can't unsee it. When you go outside and feel the sun, you'll think about the inverse square law and the 1 kilowatt of energy hitting every square meter. When you feel cold, you'll think about radiative cooling and the cosmic microwave background. When you experience winter, you'll think about the thermal properties of vacuum. When you think about your future, you'll think about how the thermal balance of the planet determines the kind of world your children will inherit. This knowledge becomes a lens. It becomes a way of seeing the world. And here's the deepest thing. Knowing why space is cold changes how you understand your own existence. You are a system that maintains order against entropy. Every moment you're alive, you're burning energy to maintain your consciousness, your thought, your awareness. You're fighting entropy. And you're winning, moment by moment, until the day you lose that fight. That should fill you with awe. Not dread, awe. You are participating in the universe's struggle against entropy. You are a node in the network of life, connected to every other living thing. All of us collectively fighting the universal tendency toward disorder. And we're winning. We're winning right now. Not forever. Never forever. But right now, consciousness exists. Awareness exists. Understanding exists. Think of it like this. The universe gave rise to the sun. The sun gave rise to planets. Planets gave rise to life. Life gave rise to consciousness. Consciousness gave rise to understanding. And now understanding is turning back on itself, understanding the mechanisms that created it. That's not just a chain of causation. That's a narrative. It's a story with you in it. You're not separate from the universe. You're an expression of it. You're the universe becoming aware of itself. And that awareness, that knowledge that you're part of something larger, that your consciousness is a rare and temporary phenomenon in an incomprehensibly vast cosmos that changes how you live. Here's the final revelation. The reason space is cold is the same reason you matter. In a universe running down toward heat death, consciousness and order are rare. They're precious. They're miraculous. The very coldness of space, the very entropy that's pulling everything apart, is what makes life, thought, and awareness meaningful. If the universe were warm forever, if entropy never increased, if disorder never won, life would be impossible. The dying universe is the prerequisite for the living universe. The cold is the condition for warmth. The darkness makes the light visible. You exist in that light. You're part of it. And knowing why space is cold is knowing, at the deepest level, why you exist and what your existence means. The ancient question, why is space so cold when the sun is so hot, turns out to be the most profound question of all. Because the answer is, your entire existence is the answer. Your consciousness, your ability to ask questions, your ability to understand the universe. That's why space is cold. Because in a cold running down universe, for a brief moment, consciousness emerged. And it's asking questions about itself. I've been explaining this to you for 3 hours and 40 minutes. I've walked you through physics and implications and cosmic perspective. But this moment right here, this understanding, this is the goal. Not to memorize facts, not to pass a test, but to understand deeply that you're part of something vast and meaningful, and to let that understanding change how you move through the world. So here's what I want you to. In the comments, I want you to write something. Not a question, not feedback about the video. I want you to write about what changed in your understanding. What shifted? What do you see differently now? How will this knowledge affect you? Share it, because someone else reading those comments will have a moment of connection. They'll realize they're not alone in feeling awe about the cosmos. They'll realize that consciousness recognizing itself is a collective experience. And before you go, I need you to do one more thing. Subscribe. Hit that button. Not for me, for yourself. For everyone who's trying to understand the cosmos. For everyone who feels the pull toward knowing. Be part of that community. Because that's where the future comes from. From people asking questions, seeking answers, and sharing them with each other. Because here's the thing nobody tells you. Understanding the universe is how you change yourself. It's how you change society. It's how you change the future. Every person who understands why space is cold is a person capable of building the technologies that harness that cold. Every person who understands entropy is a person capable of designing systems that work with entropy instead of against it. Every person who feels connected to the cosmos is a person capable of making decisions that protect their planet and their future. You're not just watching a video. You're joining a movement of consciousness becoming aware of itself. A movement of beings understanding where they come from and using that understanding to build a better future. The cold of space isn't an enemy. It's a teacher. It's teaching you that you're part of something larger. It's teaching you that you matter. It's teaching you that your existence is meaningful, precisely because it's temporary and rare. Go forward with that knowledge. Go forward knowing why space is cold. Go forward knowing what that means about you, about your planet, about your future. And in the comments, tell me what changed in you. I'm going to read every single one, because you're part of this story too. You're part of the universe understanding itself. Thank you for listening. Thank you for being conscious. Thank you for being here in this brief, beautiful moment when the universe is cold enough for life and the universe is aware enough for consciousness. That's rare. That's precious. That's you. Now go change the world. Or at least, go think a little differently about the universe you're in. Here's what ties it all together. The reason space is cold is the same reason you exist. The same reason your planet exists. The same reason the universe hasn't already reached its final heat death. It's all entropy. It's all the second law of thermodynamics. The universe started hot and ordered. It's running down, cooling, becoming more disordered. We live in the era between the hot beginning and the cold end. We're alive in the window of opportunity that entropy has given us. And understanding why space is cold is understanding why that window exists. It's understanding the fundamental framework of reality. Think of it like this. Physics is like a story. Each chapter builds on the previous ones. The inverse square law is a chapter. Thermodynamics is a chapter. Entropy is a chapter. General relativity is a chapter. Quantum mechanics is a chapter. The story they tell together is the story of the universe. The cold of space is the plot point that explains everything that comes after it. And you're reading the story right now. You're at the part where the universe is cooled enough for consciousness to emerge. And that consciousness is understanding the mechanism that created it. That's the climax of the story. That's now. We're arriving at the conclusion. We've explained the physics. We've shown the personal relevance. We've mapped out the cosmic framework. But there's one final thing I need to tell you. One final thing that brings this all home. It's about you, your significance, and what happens after you finish this video. That's the last section. When I started this video, I asked you a question. Why is space so cold when the sun is hot? By now, you understand that the question itself contains a misconception. Space isn't cold in the way your kitchen is cold when you leave the freezer door open. Space isn't cold in the way winter is cold. Space is something stranger than that. Space is cold because it's nothing. Space is cold because heat travels through it by radiation only. Space is cold Because the universe has been expanding and cooling for 13.8 billion years. Space is cold because everything in it is running down, entropically, toward a state of greater disorder. But understanding that answer changes something in you. It fundamentally rewires how you see your place in the universe. Think about what we've covered. You learned about scientists. Albert Einstein revolutionizing our understanding of energy. Hans Bethe explaining the sun. Stefan and Boltzmann quantifying radiation. Ian Parker predicting the solar wind. William Herschel discovering infrared light. Arno Penzias and Robert Wilson stumbling upon the cosmic microwave background. These weren't just names and discoveries. These were human minds working across centuries, gradually assembling the pieces of the puzzle. And now you have the whole picture. You learned about the physics, the inverse square law, thermodynamics, radiation, entropy, the cosmic microwave background. You learned why heat travels the way it does and why the vacuum is the ultimate insulator. You learned that cold is a phenomenon that depends on what you're measuring and from what reference frame. You learned about the implications. Climate change is fundamentally about disrupting the thermal balance between Earth and space. The future of human civilization might involve harnessing the cold of space as a resource. The very existence of habitable planets depends on that cold. The existence of you depends on it. You learned about the cosmic perspective. The universe is running down. You are a temporary eddy of low entropy in a river flowing toward heat death. You are stardust become conscious. You are the universe understanding itself. That's not poetic metaphor. That's physics. That's truth. And now, having understood all of this, you face a choice. You can close this video and go back to your day. You can treat this like entertainment, intellectually stimulating, but ultimately separate from your actual life. That's an option. Many people choose it. Or, and I hope this is what you choose, you can let this change you. Here's what I mean. Understanding why space is cold is understanding something fundamental about reality. It's understanding that seemingly disconnected phenomena, entropy, radiation, planetary climate, human consciousness, are all expressions of the same underlying laws. That understanding is powerful. It's the kind of understanding that, once you have it, you can't unsee it. When you go outside and feel the sun, you'll think about the inverse square law and the 1 kilowatt of energy hitting every square meter. When you feel cold, you'll think about radiative cooling and the cosmic microwave background. When you experience winter, you'll think about the thermal properties of vacuum. When you think about your future, you'll think about how the thermal balance of the planet determines the kind of world your children will inherit. This knowledge becomes a lens. It becomes a way of seeing the world. And here's the deepest thing. Knowing why space is cold changes how you understand your own existence. You are a system that maintains order against entropy. Every moment you're alive, you're burning energy to maintain your consciousness, your thought, your awareness. You're fighting entropy. And you're winning, moment by moment, until the day you lose that fight. That should fill you with awe. Not dread, awe. You are participating in the universe's struggle against entropy. You are a node in the network of life, connected to every other living thing. All of us collectively fighting the universal tendency toward disorder. And we're winning. We're winning right now. Not forever. Never forever. But right now, consciousness exists. Awareness exists. Understanding exists. Think of it like this. The universe gave rise to the sun. The sun gave rise to planets. Planets gave rise to life. Life gave rise to consciousness. Consciousness gave rise to understanding. And now understanding is turning back on itself, understanding the mechanisms that created it. That's not just a chain of causation. That's a narrative. It's a story with you in it. You're not separate from the universe. You're an expression of it. You're the universe becoming aware of itself. And that awareness, that knowledge that you're part of something larger, that your consciousness is a rare and temporary phenomenon in an incomprehensibly vast cosmos that changes how you live. Here's the final revelation. The reason space is cold is the same reason you matter. In a universe running down toward heat death, consciousness and order are rare. They're precious. They're miraculous. The very coldness of space, the very entropy that's pulling everything apart, is what makes life, thought, and awareness meaningful. If the universe were warm forever, if entropy never increased, if disorder never won, life would be impossible. The dying universe is the prerequisite for the living universe. The cold is the condition for warmth. The darkness makes the light visible. You exist in that light. You're part of it. And knowing why space is cold is knowing, at the deepest level, why you exist and what your existence means. The ancient question, why is space so cold when the sun is so hot, turns out to be the most profound question of all. Because the answer is, your entire existence is the answer. Your consciousness, your ability to ask questions, your ability to understand the universe. That's why space is cold. Because in a cold running down universe, for a brief moment, consciousness emerged. And it's asking questions about itself. I've been explaining this to you for 3 hours and 40 minutes. I've walked you through physics and implications and cosmic perspective. But this moment right here, this understanding, this is the goal. Not to memorize facts, not to pass a test, but to understand deeply that you're part of something vast and meaningful, and to let that understanding change how you move through the world. So here's what I want you to. In the comments, I want you to write something. Not a question, not feedback about the video. I want you to write about what changed in your understanding. What shifted? What do you see differently now? How will this knowledge affect you? Share it, because someone else reading those comments will have a moment of connection. They'll realize they're not alone in feeling awe about the cosmos. They'll realize that consciousness recognizing itself is a collective experience. And before you go, I need you to do one more thing. Subscribe. Hit that button. Not for me, for yourself. For everyone who's trying to understand the cosmos. For everyone who feels that pull toward knowing. Be part of that community. Because that's where the future comes from. From people asking questions, seeking answers, and sharing them with each other. Because here's the thing nobody tells you. Understanding the universe is how you change yourself. It's how you change society. It's how you change the future. Every person who understands why space is cold is a person capable of building the technologies that harness that cold. Every person who understands entropy is a person capable of designing systems that work with entropy instead of against it. Every person who feels connected to the cosmos is a person capable of making decisions that protect their planet and their future. You're not just watching a video. You're joining a movement of consciousness becoming aware of itself, a movement of beings understanding where they come from and using that understanding to build a better future. The cold of space isn't an enemy. It's a teacher. It's teaching you that you're part of something larger. It's teaching you that you matter. It's teaching you that your existence is meaningful, precisely because it's temporary and rare. Go forward with that knowledge. Go forward knowing why space is cold. Go forward knowing what that means about you, about your planet, about your future. And in the comments, tell me what changed in you. I'm going to read every single one, because you're part of this story too. You're part of the universe understanding itself. Thank you for listening. Thank you for being conscious. Thank you for being here in this brief, beautiful moment when the universe is cold enough for life and the universe is aware enough for consciousness. That's rare. That's precious. That's you. Now go change the world. Or at least, go think a little differently about the universe you're in.